we've been looking at this concept of a mole as a way of measuring an amount of atoms or molecules. It's kind of like the term dozen, where you can have a dozen roses, a dozen bagels, a dozen eggs, and it always means 12. Well, a mole is just a little bit bigger. And we said 1 mole was 6.02 times 10 to the 23rd particles. Yikes! Number one, that's a ginormous number. There's no way we could ever count that many particles. Number two, the abbreviation for mole is MOL. Woohoo, you dropped the E. Okay, so a couple things then. That we can have a mole of any kind of particle, and it always represents the same quantity. Like the term dozen, it always represents 12. A mole always represents 6.02 times 10 to the 23rd particles. However, those particles don't have the same mass, they don't have the same size or volume, and so kind of like roses and bagels and eggs, that they're different shapes and sizes. You could have a mole of feathers and you could have a mole of elephants, and you have the same number of feathers and the same number of elephants, but obviously they have very different masses and different sizes, and they have different volumes. That's then going to depend on what type of particle you're talking about. And so here we're going to refer to something called molar mass. Molar mass is the mass of 1 mole. It's in units of grams per mole. And so even though I have substances that might not have the same mass, because the particles are just different shapes and sizes, 1 mole always refers to the same quantity. So this picture is kind of cool. It gives you like a mole of aluminum, a mole of copper, a mole of sugar, a mole of salt, and it's different quantities. It's different, I should say, it's like different volumes, it's different masses. It's the same number of particles, but like visually when you look at it now, you can see that, oh yeah, like 1 mole of water molecules takes up a different amount of space than 1 mole of copper atoms, and they're going to have different masses as well. So we use this concept of molar mass a lot, especially when we eventually want to go into the lab. Molar mass then is really easy to find. You go to your periodic table. And so now we've used the periodic table in the past and we found mass, but at the time first semester we referred to the mass as like the atomic weight. Now here they're saying it's kind of a dimensionless quantity. Kind of. I mean, we just kind of used AMU, atomic mass unit. So it is kind of a generic unit. And AMU kind of arbitrarily takes the mass of a proton and puts it at 1. And then protons and neutrons end up having about the same mass. So when we were looking at carbon, and we said, oh, its mass was about 12, because its atomic number was 6, and that meant that it had 6 protons. And then since the mass was 12, it must have also meant that there were 6 neutrons. And so that AMU, atomic mass unit, kind of just arbitrarily said the mass of a proton is 1. And protons are equivalent to neutrons. Electrons have such small mass that we didn't even consider it. Well, the problem is now if I go in the lab, I can't measure in AMUs. Our electronic balances don't measure in atomic mass units. That would then mean that we had a balance that was sensitive enough to measure the mass of a proton. And that's insane. And so instead, when we go to the lab, we want to measure in grams. Our balances measure grams. That's molar mass. Molar mass is grams. But here's what we just have to be careful of. When I look at the mass of carbon and I see 12.011, I just have to know that that's not the mass of 1 carbon atom. That, again, would be insanity. Like, we can't think that 1 carbon atom weighs the equivalent of 12 paper clips. A paperclip being about a gram? That's ridiculous. We can't weigh one carbon atom. It's way too tiny. But I could weigh a mole of carbon atoms. So when I want to use that mass on the periodic table as grams, we can. We could totally use it as grams. But then we call it the molar mass. It's 12 grams per mole. So we'd say like 12.011 grams equals 1 mole. And 1 mole is 6.02 times 10 to the 23rd. In this case, carbon, its representative particle would be an atom, because carbon is an element. Oh, okay. Now that makes a little more sense, huh? It's okay to say that carbon weighs 12.011 grams, but we call it the molar mass. It's not the mass of one atom. It's the mass of a lot of atoms. 6.02 times 10 to the 23rd atoms. Now we can compare something like 1 mole of carbon to 1 mole of copper. And the molar mass of copper is over 63 grams. Yeah, that's okay. It just means that copper atoms are bigger. And copper's atomic number is 29. It's just going to have more protons, more neutrons. It's just a bigger atom. And that's okay. So the bigger atom just has more mass. And eventually then when you multiply that on a large scale, then yeah, a mole of copper atoms are going to weigh more than a mole of carbon atoms. Just like a mole of elephants would weigh more than a mole of feathers, even though it's the same number of particles. And so eventually then we can use this as another conversion factor when we want to do dimensional analysis and when we want to convert between different units. Well, earlier we were doing it with like apples and bushels and dozens, and that's fine. But now we start applying the same concept to things that feel a little more like chemistry. Atoms and molecules and moles and grams. And so here's kind of what we would see in number 8. We've got this chart. Let's see if we can fill it out. So they've got carbon. What if we had a 6-gram sample? I have 6 grams of carbon, and eventually I want to know how many moles that would be. Okay, well, we set up this dimensional analysis. It's this method of converting units. This is where all the magic happens, in this process of setting up a proportion to cancel units. The unit that you have is going to go on the bottom of your proportion. I have 6 grams of carbon, but I want to know how many moles that would be. So I start my work by putting the unit on the bottom so they cancel. Then the unit that I want goes on top. I want to know how many moles. So I put the mole on the top, and then I can just fill it in with the proper conversion. 1 mole of carbon is equivalent to about 12 grams, or 12.011, if you look on the periodic table. So these numbers are going to come from the periodic table. Now here they round it a little. Normally I don't. But in this particular little table, why don't we? Let's just see if we kind of get the concept down. Let's go ahead and round them a little bit. So for example, what if I were looking at this sulfur? And I would set it up and I'd say, okay, I have 6 grams of sulfur. So it's really important to put all the units in so that I know how to set up my proportion. All right, well, I don't want my final answer to be grams. Eventually, I want to convert to moles. Well, I'm going to need that molar mass then. The molar mass is just the mass of sulfur on your periodic table. And just for filling in this chart, let's say it's okay if we round. So let's round it to like 32. 32 grams per mole. Well, you can use that then as a conversion factor. It's 32 grams for every 1 mole. And when I put the unit in first, then I feel like I know where to put the numbers. 32 grams per 1 mole. Oh, now I can cancel, whoopsies, cancel grams. And I mean, sometimes you might have to plug it in your calculator, and maybe sometimes you get numbers that you're familiar with. So if I go 6 divided by 32, I'm looking at about, oh, I don't know, let's say 0.19. And now that would be in moles. My first number was like 6.0. It had 2 digits. So I'm just going to leave 2. And we'd say 0.19 moles. Now, obviously, like the carbon example, that one I could probably do in my head. I have 6 grams of carbon. Every 1 mole weighs 12 grams. Oh, yeah, I have half a mole. It's like saying I have 6 eggs. And every dozen is 12. Oh, yeah, I got half a dozen. Again, sometimes the numbers might not be as friendly, and then you plug it in your calculator. This would have just been 6 times 1 divided by 32, which obviously you don't have to multiply by 1. Let's try the aluminum. So if I had 6 grams of aluminum, and I don't want that in grams anymore, I want it in moles. The molar mass of aluminum is on the periodic table, and again, I'll round it, maybe just for purposes of filling out this chart. Let's say 27. Okay, so that's the molar mass. 27 grams is for 1 mole, not 1 atom. That's crazy. And so yeah, now I got my units in the right spot. Grams on the top will cancel with grams on the bottom. And we divide. 6 divided by 27. Looks good to me. Maybe we'll say about 0.22 moles. 0.22. Oh, okay, this is coming together. Let's try the last one. Oh, let's see, I think I can kind of squeeze it in here. What if I had 6 moles, oopsies, grams, hello, 6 grams of boron. And I set up my little proportion. I do not want my answer to be in grams. We're looking for moles. The unit I want goes on top. The unit that I want to cancel goes on the bottom. Then I look at my periodic table and I find boron. Its mass is about 10.8. Let's round it to 11. Let's say it's about 11 grams for 1 mole. Normally I wouldn't round, but maybe just for purposes of filling out this table. I mean, they rounded with carbon, so why not? All right, let's do this. So now I've got grams on the top, grams on the bottom. Those should cancel. And we divide. 6 divided by 11. That makes sense. I was expecting something like a little bit more than a half. So we're thinking maybe like 0.55 moles. 0.55 moles. Interesting. And so a couple things I should say that are interesting in that when I set up all these calculations, I set up every single one the same way. I had a number in grams, so on my proportion I wanted to cancel grams and put it in moles. So mole was always on the top, mass was always on the bottom. It was always the same setup. Now because I had different elements and they are different sizes, some are heavier than others, that mass number was different. But it was the same setup. It was the same calculation. Now when we did these calculations the other day, when we were converting between moles and atoms or moles and molecules, then again we had the same setup. We had the exact same proportion. But then the numbers on the proportion were the exact same numbers too, because it was just this 1 mole is always the same number of particles. here it's just that 1 mole doesn't always mean it's the same mass. These particles are different. Some are heavier, some are lighter, some are bigger, some are smaller. So it's going to be the same type of calculation, but the exact mass of the element does change a little bit. Now, the other thing that's kind of interesting about the numbers that they gave us here was that we always had a 6-gram sample. We always had 6 grams. But it turned out to be different amounts of moles. And moles is a unit that's representing a quantity of particles. So like boron had the most moles, 0.55 moles. Well, that actually kind of makes sense because boron had the smallest mass. Like boron and carbon had the smallest masses, so they end up with the most particles, the greatest moles. Well, yeah, that's like if I had 6 grams of feathers and 6 grams of, well, I wouldn't even have 6 grams of elephant. That would be like not even a portion of an elephant. But yeah, I mean, if you have the same mass, but one substance has smaller particles, well, I can get a lot more particles in 6 grams of boron than I can 6 grams of sulfur. The sulfur atoms are almost 3 times as big. So it kind of makes sense then that I wouldn't have as many sulfur atoms just because they're larger and more massive.